It is a real pleasure to be introducing today Paul Callas, who is one of our very own research fellows here at the Institute of Astrophysics, in addition to his distinguished international career. So Paul studied astronomy and physics at the University of Michigan at Ann Arbor, and did his PhD at the University of Hawaii. And then for his postdoctoral work, he did all the beautiful places, including Heidelberg, the Max Planck Institute for Astronomy there, the Space Telescope Science Institute, and UC Berkeley, where he has been an adjunct professor since 2006. And since 2019, we made official our long-standing collaborative visits that Paul has been having here at the University of Crete with a fellowship at the Institute of Astrophysics. We are thrilled to have him more regularly and formally with us. And we're delighted to hear from him today talking about exoplanetary systems. So without further ado, Paul.
Thank you very much. I'm very happy to be here and also to have this opportunity to speak to the department and to the Institute of Astrophysics. I didn't intend for this to be a review of extrasolar planets. It's more of an update on the types of projects that I'm working on and that I'm interested in. And that all has to do with the direct imaging of extrasolar planets. So imaging planetary systems has been certainly one of the oldest disciplines around. Here's Saturn seen at different wavelengths, where if you look in the infrared, you see that it's glowing hot still. And there are many questions about extrasolar planetary systems. Many are famous because people are searching for habitable planets. But with direct imaging, what we're interested in is the frequency and characteristics of the giant planets, those planets that are similar to Jupiter and Saturn. And what we want to know is how the planetary systems that we can observe vary with, for example, spectral type, multiplicity, metallicity, their birth environment. And also something that I am particularly interested in is how they dynamically evolve. Do they change position over time, or do some planetary systems remain relatively stable? Compared to other techniques, direct imaging has the advantage that we can also image very young systems, million-year-old systems, which are typically something that other techniques cannot do because of, for example, the variability of stars at that age. And ultimately, what we're interested in is understanding our own origin and how did we get here. 4.6 billion years later, we have a relatively stable planetary system with at least one planet that has life on it. But is that unusual? Is that a rare circumstance, or is it rather common in the galaxy? And that's an outstanding unanswered question. But this technique that I'm involved in, imaging, is rather difficult because stars are very bright and planets are faint, and they're swamped with the glare of the light. So this is a Hubble Space Telescope image where we've actually imaged a typical star. It's called Zeta Lep. It's 3.5 magnitude, so it's a naked eye star. It's nearby, 22 parsec is considered the solar neighborhood. And we've blocked it with a chronographic element. We've produced an artificial eclipse. Here's another piece of the chronograph here, actually, but there's another one right there. And even if we've blocked the light, we're swamped with this residual halo of what we call the point spread function. So we have to subtract it, and we have various techniques for doing that. And even when we subtract that halo, we're still left with this residual noise, sort of speckle noise. And if you look at this scale bar, 2 arcseconds, that's rather large. If this star were at 10 parsec, 2 arcseconds corresponds to 20 AU. So we can't even see anything within 20 astronomical units of this star. We really want to get as close as possible to image the planetary systems. So compared to other techniques which are plotted here, we are interested in the outer parts of extrasolar planetary systems. So this is a typical plot where we show the detected extrasolar planets as a function of mass. Here it's in terms of Jupiter masses. So this is one Jupiter mass line right here. And this is separation from the star. So if you look at the transit technique, where a planet needs to be exactly aligned in our line of sight to the star, that technique is sensitive to the planets closest to a star. It's these planets here within 1 astronomical unit of their own star. The radial velocity technique can detect planets within 5 AU roughly of a host star. And because of this problem of contrast, the direct imaging technique is studying the outer parts of planetary systems. So it's these objects right here. And so in fact, if you look at what we're trying to do with direct imaging, it's in these gray zones here. Right now we have the ability to image wide separation planets beyond 10 AU and above a Jupiter mass. And that's what we're doing up until, for example, 2025 with Gemini Planet Imager, VLT, Keck, and many other instruments. But there are some ambitious missions. For example, the Roman Space Telescope will also have a chronograph. So we hope to push our sensitivity limits inward, so we're getting planets closer to their stars. And eventually, in 20 years' time, for example, there may be missions which will be able to detect Earth-like planets through direct imaging. So there's definitely a bright future for direct imaging as we push the technological development forward. One thing I mentioned is that direct imaging probes the evolution of planetary systems. So we know that planetary systems start around stars and star-forming regions around a circumstellar disk, which requires that material in the disk flattens into a midplane so that the gas and dust there is dense enough that it can produce planetesimals and eventually planets. So this is an example of HL tau, where you see the circumstellar disk has multiple rings, and we believe this is where planetary systems, planets are forming within these rings. But at 10 million years, we have a different circumstance of where the gas has disappeared, and what we're left over is solid bodies like comets and asteroids, and they produce more dust, second generation dust, called debris disks. And at 100 million years, it becomes harder and harder to image disks. And then we end up at a giga-year or more with our solar system. And there are two pathways where I have some question marks here. And the question is, these systems here are dynamically cold. They're not asymmetric. They resemble our solar system at the present epoch. Whereas these systems here, which I'm going to talk about today, are highly distorted, as if something has happened to them. And the question is, what has dynamically happened here? How do you go from a birthplace, which is relatively dynamically quiet, to something that is dynamically active? And will this lead to our own solar system? Which pathway did our solar system take? So just to review, these disks at 1 to 3 million years are full of gas, and that's where planets will start to form. But some of the systems that I'm going to be looking at now are debris disk systems. So these are greater than 10 million years of age, roughly speaking, and they produce second generation dust. And what's interesting about debris disks is that they dynamically interact with extrasolar planets. And because of this interaction, you can infer the presence of planets just from the structure of a debris disk. So this is a simulation of a star and a planet and a system of particles. the whole simulation will run in the reference frame of the planet. So what you see is the planet, as it's orbiting the star, produces resonant features in the disk particles. This is a simulation by my colleague Mark Wyatt in Cambridge. So even if you could not detect this planet directly, what you could detect is the structure in a debris disk where you would infer the existence of a planetary system. So just to summarize, we're interested in directly detecting extrasolar planets because we want to understand the function, the properties of giant planets as a function of spectral type and semi-major axis. We want to understand how they form and how they evolve. And not only that, by looking at the debris disks with direct imaging, we can infer the existence and the dynamical history of the underlying planets. And ultimately, we want to better understand our own solar system. So a project that I've been involved with for the last 5 years is called the Gemini Planet Imager Exoplanet Survey. So we developed this instrument that achieves very high contrast and sensitivity to planetary systems from nearby stars. And we were awarded a significant amount of time on the Gemini South 8-meter telescope in Chile. And this was enough time to survey 600 stars for extrasolar planets. And in fact, this was one of the this is probably the largest systematic direct imaging exoplanet survey to date. Our European colleagues using the VLT have another instrument called Sphere, and they're also conducted a survey. My role was to lead the debris disk team with my former student, Mike Fitzgerald at UCLA. So we imaged 600 stars in the infrared. So we're not looking at reflected light from planets. What we're looking at is the infrared luminosity that emerges from young planets, younger than 100 million years, that are massive, more massive than a Jupiter mass. So we want to understand how they form. We have low resolution spectroscopy ability, so we can detect molecular constituents in their atmospheres. But my expertise is looking at the dusty debris disks. So for the debris disks, we're looking at stars that we know already have an infrared excess. And this is determined from infrared surveys, such as with the IRAS satellite, WISE, Spitzer, and others. These are space satellites that survey the sky in the infrared. We looked at 38 previously resolved debris disks. They're all young, so these are younger versions of our own planetary system. They're nearby, and because we use extreme adaptive optics, we need bright stars to lock the AO system onto the star so that it performs, so that it corrects for atmospheric distortion. And so we're looking at stars brighter than 9th magnitude. And Gemini South has a declination limit of 25 degrees north. In other words, we can't observe anything more north than plus 25 degrees. And also, the field of view is rather small, but has a radius of 1.8 arc seconds. So here's a quick video that summarizes what we did in 5 years. So I think I'm going to mute the music here because it's rather loud. Well, I can't do that, actually. So you're going to have to listen to the soundtrack that I put. And I apologize if the music isn't what you like. Okay, so every image here is a separate target, and this is the southern sky. The symbols here are the size of the symbols represents how close a star is to us, and the red symbols are the debris disks that we've imaged. If a symbol is gray, we did not detect an extrasolar planet around it. If a symbol is blue, we did detect an exoplanet. So these are the blues are the exoplanets, grays are non-detections, and red are debris disk detection. Okay, so you'll notice that this star here has been observed multiple times. Each circle represents a separate observation. And the reason for that is that we found an extrasolar planet, and what we want to understand is its orbital elements. So we image it multiple times, year after year, several times a year, in fact, so that we can track its motion around the star and determine its properties. And we're going to see that extrasolar planet, 51 Arri b, right here. There you go. Here's a sequence of images showing its orbit around the star. So here's our entire sample, and here are the many debris disks that we imaged. The whole survey for debris disks was written up by our postdoc Tom Esposito, doing incredible work to reduce all these data, and this was just published recently. And this is the sample we had shown here, and the actual detections are here in blue. So most of the detections, a large fraction of them, were actually in the SCO-SEN-OB association, which is a young association between 10 and 17 million years old, and it's slightly over 100 parsec away from the sun. And then you can see the other properties here. The median age of our sample was 45 million years. And I'm going to keep going, skip some of these details. We detected 26 debris disks, and 7 were new discoveries. And here is our image gallery of debris disks. And it's a rather remarkable image gallery. I think no other survey has produced so many images of planetary systems in their debris disk phase. This is, again, H-band, and we're looking at polarized light, because when light from the star reflects off these dust particles, it becomes polarized. And you can see that what we've detected is very interesting structures, circular structures. And the scale here depends on how far a star is from the sun. So for AUMIC, which is only 10 parsec away, Mars, our own Mars, would be detected here. Whereas for some stars farther away, like HD 32297 at roughly 100 parsec, we would be detecting Neptunes here. And so we see many ring-like structures. And in fact, even when you see an edge-on disk like this, you can tell there's a central depletion of material near the star. So we think the depletion that you see here, HR 4796A is a wonderful example, a really beautiful system. We think that this depletion is because a planet, or more than one planet, has formed inside this region. The distance from here to the edge of the disk is roughly 80 astronomical units in this case. So we think that in this case, you have a planetary system 80 astronomical units in radius that is clearing out the material. These were actually new discoveries not previously known in the literature that we made with the Gemini Planet Imager survey. So one thing we can do is measure the sizes of these planetary systems. So I already mentioned that for 4796A, what's been discovered is that even though we don't directly detect the planets in here, we know the size of the planetary system is roughly 80 AU in radius. And we also have complementary data from ALMA. ALMA is a millimeter submillimeter observatory that detects thermal emission from millimeter-sized grains, whereas what we're sensitive to in the near-infrared is micron-sized grains. And for example, here is one of the science results from this large paper, where we compared the sizes of planetary systems detected with ALMA versus what we detected in the near-infrared with GPIE. And what was published by Luca Matra 2018, is that when you look at the sizes of planetary systems, so this is radius here, the inner radius of a debris disk versus stellar luminosity. So here you have solar type stars and the A type stars here. What they found with ALMA is that the sizes of these planetary systems increase with stellar mass. But we didn't exactly find that. We did not find a significant correlation of the sizes of planetary systems with stellar mass. So this was our result right here, which is not a significant slope. Here is this dashed line is the ALMA result. But what was very interesting and puzzling is the large scatter in radii that we detected. So these are all different planetary systems that exist around similar spectral type stars. And some have inner radii as small as 13 AU, and others are as large as 87 AU. So how do you explain a group of planetary systems roughly the same age where the size of their inner holes has such a large variation? So obviously there can be quite a bit of diversity in how planetary systems evolve. You have this large scatter in radii. And so this comes back to this question of what happens between 1 and 10 million years that will create a different planetary system, and ultimately, which path did our solar system take? And the system I'm going to talk about in detail as a case study is this one, HD 106906, and then later Fomalhaut, which are along what I believe are the perturbed pathways to planetary systems. So in this case, the inner disk was discovered with the Gemini Planet Imager, shown right here. And this scale from the star to the edge of the disk is 50 astronomical units. So we believe the size of the planetary system is roughly 50 astronomical units. But with the Hubble Space Telescope, what we discovered is a highly asymmetric debris disk that extends out to at least 500 AU. What's exciting about this planetary system, and unique, is that it has an exterior extrasolar planet called 106906b. And that's it. This is a common proper motion companion to 106906, but it's located outside of the disk and inclined by roughly 22 degrees away from the disk midplane. And this presents quite a few mysteries. For example, is the planet still bound to the system, and is it responsible dynamically for the large-scale asymmetries we see here? And how did it even get there? Did it form in situ? In other words, did it, for example, collapse like a star and become a planet far from HT 106906? Or was its origin, did it originate in the circumstellar disk within 50 astronomical units of the star, and then somehow it got ejected to this position here? This position here is 737 astronomical units from the star, which, by the way, is very dynamically interesting because it's a spectroscopic binary. In fact, the star is is actually a binary of 2 F stars. So theorists have looked into the possibility that the planet does account for these debris disk asymmetries. First, Jilkova et al. Published these simulations. These are simulations where you have an eccentric planet interacting with disk material over time. So this is the initial condition here after 0.2 million years, after 500,000 years, after 0.8 million years. Neswold et al. Showed that, in fact, you could get the length asymmetry of the disk by having an eccentric and slightly inclined planet to the system. And the same is true for Laetitia Rodet's model, where she has a planet perturbing the disk material and producing this asymmetry. The star is here, but what you get is an asymmetric disk just as observed. So I'm going to focus a little bit on Laetitia Rodet's model. She was a student of Hervé Buste in Grenoble. And in this model, this is what she thinks happened. We know that the central star is a binary. And what she thinks is that the planet, shown here as this red dot, migrated due to interaction with the disk material inwards towards an unstable resonance with the binary. So here is a plot of the planet's semi-major axis as a function of time. And over time, in the protoplanetary phase, when there's plenty of gas and dust, the planet migrated inward and hit a 1:6 resonance with the stellar binary. That produced an instability so that eccentricity and semi-major axis and inclination can oscillate very rapidly. That instability will cause the planet to achieve high eccentricities, so high that the planet should eventually be ejected. Except it can become long-lived if another perturbation happens, and that is if you have a stellar flyby. A passing star can perturb the planet at apastron, imparting just enough energy so that the planet's periastron increases. Periastron, if it's too close to the star, is unstable and will eventually be ejected. So you have to increase the periastron and create a new orbit that will become long-lived, and that's this blue line. And here's another simulation where I have just a toy disk, where I have a debris disk here, and I have a highly eccentric planet that is supposed to be 106 906b. And so let's take a look at this. So right here, we have a planet where periastron is too close to the binary. So what if you have a stellar flyby that will raise the periastron distance by a few astronomical units? You'll see what happens in these two separate cases. If you don't raise periastron, you end up with an orbit that ejects the planet. It's hyperbolic. But if you do have a stellar flyby, then you have a long-lived system. Okay, so the question is, do we have any evidence for a stellar flyby? And that's what we did with Rob DeRosa, former postdoc at Berkeley, now an ESO scientist in Santiago. What we did is we took the Gaia DR2 catalog, which has the positions, parallaxes, and proper motions of all the stars in SCO-SEN. Not all the stars, 500 stars in SCO-SEN. And we basically traced back the motions of these stars to see if any of these SCO-SEN members had a flyby of 106 906b, of not B, but the star 106 906. And the quantity you find is the closest approach distance and the closest approach time in the past. And sure enough, what we discovered is that an F star and a G star, which themselves are a binary themselves, passed within a parsec of 106 906b, roughly 2.5 million years ago. And what's very interesting about this flyby is that it was also, because the Gaia data have so much information, we can also calculate the geometry of the flyby. So that here what we're calculating is the flyby with respect to the disk plane. So that what we see here is that the flyby of these two stars was within 10 degrees of the disk midplane. Now, so let me show you the next slide. So here they are. Here's 106 906b. And here are the flyby stars right here. The projected separation is 1 parsec, except that these stars are also 10 parsec in the background at the current epoch. But is this close enough to perturb 106906b, the planet? So this is half a parsec here, whereas the planet is much closer to its host star. So in this calculation, we try to understand how much the periastron distance would be raised by this flyby, depending on how close a flyby is, and also on how eccentric the planet is. And this is the color coding here. So in other words, if we want to raise the periastron distance by 1 AU, we need to have a relatively close flyby. So this is 10 to the minus 1 parsec. This is 2000 AU. But really, the flyby that we detected was in this region here. So it's possible for periastron to be raised with this given flyby, which was at half a parsec, but you need a very eccentric orbit for 106906b. Okay. So what is the orbit of 106906b? Is it highly eccentric so that it could have been perturbed by a distant flyby? Or is it more circular, in which case these are not the flyby stars that perturb the planet? Oh, so I just wanted to review comparing 106906 to our own solar system. So we have a binary star in the middle, and here's a scale bar going out in astronomical units. Earth, obviously, is at 1 astronomical unit. And we have our giant planet region here, and then the Kuiper belt. What we see with 106906b is the debris belt and the 11 Jupiter mass planet 106906b exterior to the debris belt. And here is the flyby distance of roughly half a parsec. The solar system also has experienced flybys. The most recent is actually called Scholz's star, which was discovered with WISE. And that flyby happened 70,000 years ago, and the closest approach was a quarter parsec, or 52,000 AU. Okay, so these flybys also occur with our solar system. So to just summarize what we've discovered so far is that we're studying the 106906 planetary system. We did discover a flyby that's near coplanar with the disk, which could have perturbed the planet, except we don't know the orbit of the planet. And so this is work that I've been involved in most recently to determine the orbit of 106906b. The problem is that at 737 AU, the orbital period is 12,000 years. And that corresponds to a velocity of 1.8 kilometers per second. And that corresponds to 37 milliarc seconds in a 10-year time span. So is this a feasible project to do? Can you get this type of astrometry over 10 years? And here are the data that were available. We have data from 2004 with the advanced camera for surveys. This camera actually broke, so we can't use it again. But back in 2004, we have an epoch where we can do the astrometry. And it has very good sampling of the Hubble point spread function of 25 milliarc seconds per pixel. Then we have 14 years later, a group of observations, 12 to 14 years later, a group of observations by the Wide Field Camera 3 in the infrared, where the pixels are 128 milliarc seconds, but also a STIS program that I'm the principal investigator for, where STIS has 51 milliarc seconds per pixel. So this becomes a very challenging astrometry project because the motion that we're expecting, 37 milliarc seconds, is roughly the size of a pixel. And we're using different instruments, and this is occurring over more than 10 years time span. So this is relatively difficult. And the problem is all these images are block the central star. With the advanced camera for surveys, we're using a coronagraph. So HD 106-906, the binary star, the spectroscopic binary, is hidden behind this mask. So it's very difficult to get precise astrometry from the planet, which you can see here, circled right here, to the star. And then many years later, 11 years later, we have STIS, where again, the star is being blocked by a bar. This is an occulting bar, and here is the planet. And then with WIFC3IR, we're not using our coronagraph, but the central binary is heavily saturated. And here's the scale again. So we're missing all this information in order to do astrometry on the central star to get the relative motion of the star, of the planet relative to the star. We're trying to determine its orbital motion. So fortunately, many of these field stars were also in the Gaia DR2 catalog. So what we can do is determine where 106-906, the central binary, is located relative to the field stars. And this is what we did. It was a very sophisticated work, and we eventually detected orbital motion. And all this work was done by Rob DeRosa and Meiji Jungen in Berkeley. They put in a tremendous amount of effort to do this astrometry, and we detected orbital motion. And it was really a fantastic accomplishment, and we weren't even sure if this was going to be possible when we started the project. And what we detect is 32 milliarc second eastward motion from the 2004 epoch to the 2016-2018 epoch, where the most constraining data are from HST STIS. So here are the smaller error bars from STIS. So we got this orbit of this distant detached exosolar planet. The projected, now we don't have the three-dimensional velocity. We don't have a radial velocity for 106-906b. All we have is the sky plane motion. That gives a projected velocity of 1.2 kilometers per second, which is less than half of the escape velocity. So we do think that 106-906b is bound. It would be very unlikely if it had some tremendous motion into or out of the sky plane. And we can fit this orbit using, here we used Orbitize, a software package that you can find with in Blunt et al. 2017-2019. And so here's what we found. That very important is that the periastron distance is 500 AU. So it's actually exterior to the planetary system. So in fact, this orbit is long-lived. It is no longer under the influence of the central binary. The periastron distance has been raised from some smaller value out to 510 AU. The orbital period is 15,000 AU, semi-major axis 850 AU. And it's a rather eccentric 0.44. And it's also inclined relative to the disk midplane by roughly 40 degrees. And when you look back at the models we started out with Nesvold et al., in her simulation, she assumed 700 AU for semi-major axis, slightly higher inclination and a slightly higher eccentricity and a slightly lower mutual inclination. But this shows that this giant planet, 106-906b, is likely the source of the dynamical disturbance occurring with the extended debris disk. Okay, so let's just review what we knew earlier was just the separation between the star and 10696b. But now we have actually an estimate for its orbital elements. And this is tremendously powerful because now we can really compare it to our solar system. 10696b is now, we know, detached from the inner planetary region. So what it resembles is the detached objects of our own solar system. Detached objects are those outer solar system objects that never interact with our planetary system as defined by the orbit of Neptune. So here in this plot to the right, this is the orbit of Neptune at 30 astronomical units. And people who search for Kuiper Belt objects like Mike Brown and Chad Trujillo and Scott Shepard and others have discovered objects like Sedna. Sedna never approaches the orbit of Neptune. And in fact, it's a mystery of how Sedna formed. How did it become detached from the planetary region? Let's take a look at the outer solar system plotted here in a review article by Konstantin Batygin. This plot shows the eccentricities of solar system objects versus semi-major axis. And so here you have 30 AU, the orbit of Neptune. And you have the classical Kuiper Belt here at 40 astronomical units, which is influenced by resonances with Neptune. Q is the periastra of objects. So all of these objects that have periastra less than 38 AU are under the influence of Neptune. But if periastron is greater than 38 AU, you have a detached Kuiper Belt object. And so here is Sedna, for example. And where does 10696b now fall? And it's right here. So we know that 10696b is detached like these Kuiper Belt objects, except it has a much higher mass. And you may have heard that we believe there could be an outer solar system planet called Planet 9 that influences the orbital elements of these objects. It's a hypothetical planet of roughly 10 Earth masses called Planet 9. And you can compare the properties of the hypothetical Planet 9 to HD 10696b. Planet 9 is supposed to have an orbital period between 8 and 23,000 years, and 16906b has a 15,000 year orbital period. Semi-major axis is roughly the same. Perihelion is also detached for Planet 9. The eccentricity of the hypothetical Planet 9 is also in the range of what we found for 10696b. And also Planet 9 is supposed to be inclined relative to the orbital plane of the solar system. Of course, there are differences. 10696b is an 11 Jupiter mass planet, whereas Planet 9 is supposed to be several tens of Earth masses. But essentially, you can understand now how a Planet 9 could exist around our solar system. And in fact, this has been a mystery of how Planet 9 formed, if it exists. One model is that you have in situ formation, that Planet 9 formed at these large radii, but that's unlikely because there isn't enough material in a circumstellar disk to form a 10 Earth mass planet farther out. Another scenario is that you have formation of Planet 9 among the giant planets, and this 10 Earth mass planet was likely ejected, and then its orbit was stabilized by a stellar flyby, just like we've been discussing with 10696b. And the third option is that it was captured. Planet 9 was captured by our sun when it was ejected from another planetary system. So this is very intriguing. What we've discovered with 10696b is that the ejection scenario and stabilization by a passing star can occur very early in the dynamical evolution of a solar system. So if you remember this plot here, 10696b is just 15 million years old. So all the action happened in this time period between 1 and 10 million years. And so too, this could have been what happened in our own solar system, that this long-lived orbit for Planet 9 was established over 4.6 gigayears ago. Okay, so here is where we started earlier in the talk, and there are questions about which pathways our solar system took. And it's entirely possible it took the lower disturbed pathway here. And here are some of the planets that we've imaged so far. These are all GPIES simulations. And so far I've talked about 106, 906b. But next I want to finish up my talk by talking about Fomalhaut b, which is this object right here. Fomalhaut b also has a highly eccentric orbit. The star is older, 440 million years old. And this orbit is rather mysterious. And in fact, the nature of Fomalhaut b is a mystery. In the discovery paper, this should say 2008 here, I suggested that Fomalhaut b could be, there are two options for what we're seeing. Is Fomalhaut b a planet where what we're seeing is a giant ring system around the planet? So in this illustration, you don't have a relatively small ring system like you see around Saturn. You have a giant ring system, at least 40 planetary radii. Because Fomalhaut b was discovered in the optical, and its optical luminosity was rather large, given that we did not detect Fomalhaut b in the infrared. So we know it's less than a Jupiter mass planet, but it's optically bright. And an explanation for that could be that it's a Saturn-like planet, where what we're seeing is reflected light from its ring system. Another idea is that we're seeing the mutual destruction of two colliding planetesimals. And this collision created a dust cloud. And again, what we're seeing is reflected light from dust. But it's not from a planetary ring system. All we're seeing is planetesimals colliding. One prediction, so here is, on the left is the HST image of Fomalhaut's dust belt, which is at 140 AU radius. Here's Fomalhaut b, and here is its highly eccentric orbit traced here. But if Fomalhaut b were the result of a collision between two planetesimals, the cloud of dust shears very rapidly. So here's a simulation where we start, where this point is the collision point. This is at 50 years, 100 years, 150 years, 200 years. So that by 200 years, the cloud has expanded due to the differential gravity of particles. So as this cloud passes through periastron, some particles are on shorter period orbits, other particles are on longer period orbits, and this causes the cloud to spread out. So the problem is we haven't resolved Fomalhaut b. So the more likely explanation is that you have a long-lived system that can be observed over time, whereas the colliding planetesimals are short-lived phenomena. So you need to be extremely lucky to observe it. So I did propose both of these alternatives, but I favored the planetary hypothesis based on these on the argument that this is a long-lived phenomena compared to a random collision. So what's new is a paper where András Gaspar and George Ricci looked at all the archival HST data and concluded that Fomalhaut b is expanding in size, becoming fainter, and actually disappears in 2014. And this is what they showed in the paper. They analyzed the old 2004 data where I discovered Fomalhaut b in the first place, And this is where they detected Fomalhaut B. It's this speckle, this little dot here. At different wavelengths. Here is at 435W, and here it is in 606W. So this is in the optical. And this is in 2006. This is in 2004. These detections have actually been confirmed by 2 other groups independently. So the discovery of Fomalhaut B has been confirmed by me and 3 other groups completely independently. So it's not noise. It's a real object that is a common proper motion companion to the star. Here are the STIS data obtained in 2010, which I published in 2013. Here's a 2012 detection of Fomalhaut B. And what they're saying is that in 2013, all of a sudden, the light seems to be spread out as if you have a cloud of dust that is being sheared, gravitationally sheared, or due to radiation pressure, is being smeared out in space. And then they're saying that in 2014, there is no detection. And this is where Fomalhaut B should be, except there's nothing there. So they have announced that Fomalhaut B has disappeared. So I'm working on the same data. I'm the PI of the observations. And for 2013, my strategy was to ask my former student, Jason Wang, who is an expert in reducing and analyzing high contrast imaging data, to independently reduce the data from me. So when I look at the 2013 data, I detect Fomalhaut B and I see it as a point source. So I disagree with the Gaspar and Ricci result that Fomalhaut B has become extended. And independently from me, Jason Wang, using his own techniques, discovered that Fomalhaut B continues to be a point source in 2013. So for the 2014 data, has Fomalhaut B disappeared? And here's a test that I did where I said, if Fomalhaut B is the same brightness in 2014 as it was in 2012 and 2013, would it have been detected? And the problem is, I know that the data from 2014 are noisier, partially because the integration time is half of the previous epochs. So I did an injection and recovery experiment where you take the data and you expect Fomalhaut B to be somewhere in this box. And you inject an artificial point source, the same brightness as Fomalhaut B, into the data and see if you can recover it. Is it detectable? And the answer is these data are so much noisier than the previous epochs that only 33% of the time is Fomalhaut B detected. So that means I don't think Fomalhaut B has disappeared. It's just that the 2014 epoch is too noisy for the detection to likely have been made. But one thing we do agree is that Fomalhaut B seems to be changing position over time. So this is our astrometry for the 2013 epoch. And here are the previous epochs. So this is in the sky plane. Fomalhaut B over time has been moving along to the north roughly, but seems to be deviating to the west. And this is also confirmed with Jason Wang's independent astrometry. If you deproject the whole system, so we've deprojected as if the system is face on, Fomalhaut B is right here, and it looks like Fomalhaut B is actually curving around so that between the 2012 and 2013 epoch, it's going on a radial trajectory. In the Gaspar and Ricci model, this is possible because a dust cloud gets influenced by radiation pressure and starts moving out in a radial direction. So in their model, they have 200-kilometer asteroids colliding. The collision happens in 2004. Fomalhaut B would be above the detection level for only a decade. And we expect such collisions would happen once every 150,000 to 500,000 years if we assume the volume density of objects within the dust belt. The problem with this model is that it means that I was extremely lucky to have seen Fomalhaut B because it's an event that only happens every several 100,000 years, and the time scale for the phenomena to be observable is a decade. So that if I had pointed the Hubble Space Telescope at Fomalhaut B in 2004, I would have detected it. But if I was just a few years late or a few years early, nothing would have been discovered. So this is conceptually a problem. We need a more long-lived scenario for Fomalhaut B. So one idea is that you have a planet in orbit around Fomalhaut, and it disrupts gravitationally a weak body like a comet, producing something like the Shoemaker-Levy 9 event back in 1995. So you have a breakup of a comet that comes close to a planet, and that explains why we have the Fomalhaut B phenomena. What I'm actually looking at, and this is work in progress, is the idea that you have a planet in the Fomalhaut system. It is nested, its orbit is nested within the dust belt, but the planet itself has a moon system, which I'm showing here. And one of the moons has a very eccentric orbit. So that periodically, when it comes near its periaps, it encounters other material orbiting the planet. And collisions during periaps produce a fresh dust cloud of submicron grains. So that the planet produces periodically outbursts of dust. So that in 2004 and 2006, we were witnessing this outburst of dust just happening. And now we're seeing that dust cloud departing the system due to radiation pressure. So because I'm running out of time, I'm gonna go to almost my last slides. So what's exciting, what I like about my model with the eccentric moon idea is that it may explain another system where we see outflowing features. AUMIC. AUMIC is at 10 parsec, it's an M dwarf, and the debris disk is seen near edge-on. And what's been discovered through multi-epoch high-resolution imaging with SPHERE and the Hubble Space Telescope are these dust clumps that are moving outward. So here's 2014, and here's 2011, here's 2010. So you see this clump is moving outward over time. And the source of this clump is a mystery, except it can be modeled if you have a parent body that periodically ejects a cloud of dust. And this has not been actually explained. How does this happen? So it could be that what we're seeing with Fomalhaut B is the same phenomena as we see with AUMIC, except at different viewing inclinations. Here we see a compact source in the edge-on case, whereas Fomalhaut B is at an inclination of 66 degrees. Okay, to summarize, we started out with this debris disk survey where we mapped the architecture of 26 debris disk systems out of 104 stars that we surveyed. And each one of these systems reveals the dynamical history of a planetary system. I focused on the 106-906 system, where we first identified the flybys that could have perturbed the planet 106-906b, detaching it from its from influence from the central binary. Except in 2019, we hadn't determined its orbit yet. So the follow-up study was this tremendous achievement of actually getting an estimate for its orbit, showing that, in fact, periastron is detached from the planet, from the central binary, and therefore invites comparisons to Planet 9. And then I talked about the recent results of Fomalhaut, where we continue to see it has some puzzling properties. I don't think it has disappeared, But what we think is that it does represent a dust cloud, except that the source of the dust cloud is probably related to the existence of a planet that has yet to be detected. All right, thank you very much.
Thank you very much, Paul. We do have time for a few questions for Paul. Questions?
Can I ask one, Baso?
Of course. Nico.
Here. Okay. Paul, thank you very much for a very exciting talk and really interesting results you have produced since the last time that we gave a seminar on this topic. So tremendous progress on the subject. My question is the following. Maybe you said it and I did not catch it. So here's the question. This planet HD 106 blah blah b
Yes.
with the which is 700 parsec and so on, it has an eccentric orbit.
Yeah.
Now, did you say, and if not, can you explain now, how did it acquire such an eccentric orbit in the first place?
Okay, first I have to say that I'm didn't bring my charger and I may be cut off with the question time. But the answer is the Rodet model, where you have a dynamical instability with the central binary, eccentric binary star. The star has two Fs, the central binary is two F stars, and the eccentricity of that orbit is 0.6 or 0.7. So there are unstable resonances in the system so that the planet may have acquired its eccentricity in a brief period of instability with the central binary. This
planet was formed, in the opinion of the people who work on it, as a planet of the binary.
It was a planet in the disk, in the circumbinary disk. That is the idea.
In the circumbinary disk. Okay. Okay. Then I can understand how it can be kicked off by some instability. Okay. Okay. Fine. Thank you.
One more question for Paul while the battery lasts. Anybody? Yes, Dimitri?
Hi, Paul. Thanks very much for your talk. You attributed the inner holes in these disks that you described in the presence of planets. Do observations exclude the presence of low mass stars or even substellar objects?
Yes, in general, we would have detected any star or any brown dwarf is that what you're saying? Yeah. No, we would have detected brown dwarf mass easily in those regions, easily.
Okay.
So we can exclude that.
Mm-hmm. Thank you.
Other questions? Okay, so let me ask one quick one, Paul. So what's the future observations of Fomalhaut B? Do you think there is more to be found out?
Yes, I have a couple more slides on that actually. But with JWST, so we're saying that a planet is there that's less than a Jupiter mass. JWST will be sensitive to that planet and will be, Fomalhaut is a guaranteed time observation with JWST. So that's going to happen with JWST. From my end, I'm trying to get new HST observations to show that the optical cloud has not disappeared, and to track its motion in an epoch in 2021, for example.
Wonderful. Okay, so given that we're running against the battery, and if there are no other pressing questions, let me thank Paul once more very, very much for this wonderful talk. It's always very nice to hear from you. And until next time, thank you, everybody, and goodbye.
Thank you very much.